In this video, we're going to be solving a satellite circular motion problem involving the Earth and the Moon. And then we're going to solve for the orbital velocity, and then eventually the period of the Moon. So although there are two specific objects in this case, the Earth and the Moon, this applies to any kind of satellite question. So one main body with something revolving around it. So we have the mass of the Moon, the mass of the Earth, and the r, which is the separation distance between the two. So that r value is actually the separation distance between the center of gravity between the two objects. So r isn't the separation distance just from the surface of the Earth to the surface of the Moon. It's a distance from one center of gravity to the other center of gravity. So in certain cases, you may have to take that into consideration. In this case, our r value is already that distance. Okay, so let's get started. In this case, we have two objects that have an FG, force of gravity, pulling in towards each other. We have the force of gravity of the Earth being pulled this way, and then we have an equal and opposite force on the Moon being pulled in that way. Now, because the Earth is significantly larger in mass, the Moon is the one that seems to get most of the effect as far as the acceleration and velocity, but both of them get the equal force of gravity. So that force of gravity for the Moon is pointing towards the center of its orbit. So that is the centripetal force. So the force of gravity is equal to the centripetal force, and the force of gravity is gmm over r squared. And the centripetal force is mv squared over r. So one of the first things we can do is we can cancel out one of the r's. And the second thing is we can cancel out one of the m's, but you want to be careful which m you are canceling out. Remember, we're focusing on the Moon revolving around the Earth. So we're going to cancel out the m, which is the mass of the Moon. So this m1 is the mass of the Earth. Turns out that the actual mass of the satellite is insignificant. It gets canceled out. So we have our gravitation constant, which is 6.67 times 10 to the negative 11th times the mass of the Earth. And then divided by the radius, and the radius is 3.84 times 10 to the 5th kilometers. So if we convert that, we get 3.84 times 10 to the 8th meters. So that's something to watch out for because the standard unit for mass is kilograms. So that one is in the correct unit, but if it's in kilometers, you definitely want to convert that into meters. Okay, so all of this equals mv squared over r, but the m and the r got canceled out, which is nice. So we only have a v squared over here. So what you're basically doing is you are square rooting this entire side. So after multiplying these two and then dividing it by the r value, we get a velocity of 1018.32. And that's our orbital velocity of our satellite, which is the Moon. Now, second thing we're going to take a look at is we're going to solve for the period of the Moon, so the amount of time it takes to complete its orbit. And the way you do that is you take that velocity and then you set it equal to 2 pi r, and we know our r value, so we can just go ahead and plug it in, 3.84 times 10 to the 8th meters over t. Okay, so whenever you're solving for a period, you're going to use the 2 pi r over t formula. 2 pi r is your circumference of your circle, so we're assuming it's uniform circular motion, divided by capital T, the period of that orbit. And if you just cross multiply these two, then you get your answer. And then your capital T, which is your period, comes out to about 2.37 times 10 to the 6th seconds. Okay, and there's our second answer right there. I'm going to go ahead and do one final thing with our period. So the accepted period of a revolution for the moon is 27.3 days. So let's go ahead and take our time and see if that works out. So we have a time of 2.37 times 10 to the 6th seconds, and there are 60 seconds in a minute, and there are 60 minutes in 1 hour, and there are 24 hours in 1 day. So when we do that calculation, basically what I do is I take 2.37 times 10 to the 6th and then divide it by the product of these three numbers combined. If you want, you can divide them each individually, but I usually just take one big numerator, which is just this number because we have all ones across the top, divided by the product of this bottom number right here. And then our period then gets converted into days, and we end up getting 27.43 days, which is pretty close to the accepted value of 27.3 days. But within that calculation over here, we did a little bit of rounding, and there's some other factors that affect the period of the moon that makes it not a uniform circle. But either way, that is how you do the conversion to get the period in days. So to sum things up, when you're doing a satellite problem, you set that force of gravity equal to the centripetal force, and then you will have some cancellations. You'll be able to cancel out the mass of the satellite itself, but the thing that it's revolving around does not get canceled out. One of your radiuses, one of your radii get canceled out, and then you have v squared equals gm over r, and then from there you can solve for a velocity. If you need to find some other specific details, such as the period, then you can set that velocity equal to 2 pi r over t, and then go ahead and solve for that period. So I hope that was helpful in helping you solve for and understand a satellite problem. Thank you for watching and listening.